Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Hey, welcome back. Today I want to talk about grouping. We are seeing a lot of excellent demonstrations of good workmanship by electricians, but what seems to be a fundamental flaw in this work is where they are strapping all of these conductors together to give it a really good looking result. So a couple of examples that I'm going to show here. So this consumer unit installed here, all the wiring was strapped together on the tray. In the consumer unit as well, they were all strapped together, all the lines, all the neutrals, and it creates a nice looking result. But what I need to talk about is how this impacts the installation's design and how we're supposed to, intend on this to be done. Now, if we have intended for this to be done, great. The designer has accommodated this and it's going to compensate for any impact. But sometimes the designer hasn't thought this ahead, and the contractor doing the installs decided to make the job look good, and they've done it themselves, and that can be a problem. Some other examples we have here, where we have it going around the edges. So we've got lots of space around the devices, and all the cables are brought in to close confined areas around the edges. Here's another example, all tied together. Here's another one. And these look like neat jobs. These look like good, neat consumer units. The problem is what impact is this going to have? Here's another one. Here's another one. And even this. I mean, look at this workmanship around this consumer unit here. Yeah, but all of the cables are tied together. So, what kind of impact does this have? Well, first thing we need to understand is the capacities for conductors. So if we were to assume that these cables were the standard off-the-shelf 70 degree thermoplastic, we need to remember that 70 degrees is the limit operating temperature of those conductors. We have a regulation that tells us this. Is it this one? Yep, 523.1. This tells us about the limiting temperature at the conductor for thermoplastic insulation, 70 degrees. So when we say a cable can carry X amount of current, what we're really saying is it can carry that current from a baseline to get to 70 degrees. The problem is, are there any other factors that adjust this? From an ambient temperature perspective, let me get rid of that. If I was to say ambient temperature, which isn't really what we're going to cover today, but if I was to get a pen here, and I'll also say, right, well, down here is temperature, along here is time, then up to maybe an hour under load, we can expect a conductor to go from its cool temperature up to its final operating temperature. So let's say that this is like 0 degrees, and then maybe here we have the 30. And then maybe here we are, this is where my scales can be completely off, 40, 50, 60, and 70 degrees. So if I was to say, let's go with an example. I'll go to table 4D2A. Now this table here is for multi-core cables, non-armoured. It's a bit like the twin and earth cable, but it's for multi-cores, not the flat profiles. If we look here at the reference method C column, and then we look down the single phase column under that. So it's column number 6. Reference method C, click direct, then 1 2-core cable, column 6. If we go down to a 2.5mm cable, it will tell us a 2.5mm cable equals 27 amp. Okay, tells us 27 amp when installed in that reference method. And that reference method is reference method C, which is the clipped direct. And that's my wife bringing me a cup of tea. So, hey. Thank you, my love. Fine. Cheers. Right. She's trying to keep me well. So reference method C is click direct. I'm using that as an example because that's probably the most suitable method to use here. So when you look at the table, you can see at the very, very top right of the table, it actually tells us the ambient temperature is 30 degrees. So that's kind of like the starting point for the conductor's environment. And there is a conductor operating temperature of 70. So what we're really saying is when the conductor is not under any load, it's humming in an ambient temperature of about 30 degrees. Let me get rid of this for a minute, and you can see where I'm marking that. So I've marked that there at 30 degrees. And what this is saying is under a period of time under load, it wants to get to no more than 70. So let's say that under load, it kind of increases like this, but then it kind of gets to a idle point here. And we want to go no higher than that. So the question really is how much current would it take for us to get from the 30 up to the 70? And with the reference method being reference method C, that's simply 27 amp. Now, if we were to adjust that baseline, so let's say the ambient temperature was 20 degrees further down there, I'll go to another color, you can see that we still can't go over 70. So if I apply 27 amp to that, my curve would actually end up here. It would look something like that. And I wouldn't, that would be a 27 amp result. And I could put more on that. So I can actually, if it's going to be at 20 degrees, I can apply more current, to get up to 70. Similarly, if I was at 40 degrees, I'd have a lower amount of current because the fundamental point here is I must not, so that's the amount of current for 40. The fundamental here is I must not go over the 70 degree limiting temperature. And we accommodate this with our design with the rating factor of CA, which is in table 4B1. 4B1 in the regulations. And you'll notice when you look in table 4B1 that 30 degrees, they're all 1, meaning 30 degrees is unity, meaning the cable current carrying capacities in table 4D2A are given at 30 degree ambient. If we go just from that, we have to adjust those temperatures by using that CA factor. But that's one impact, but the impact I want to concentrate on here is still focusing on the fact that the conductor must not be more than 70 degrees under load if it's thermoplastic. But what happens when I have a conductor under load? Well, it's designed to give off some level of thermal losses. Okay, and that's intended. Obviously, a preview of part 8, which will come in Amendment 1, will start, and you'll see this in Appendix 17 right now, is it starts to say, oh, if we make our cables bigger on purpose, then we're reducing thermal losses, which is an energy efficiency thing. That's something that's currently in debate, but all we need to know is that if I have a cable such as 27 amp, 2.5 mil, which is the example we're using here, 2.5 mil equals 27 amp, and don't forget that was reference method C. That's designed to have some level of thermal losses. That's fine. The problem is what happens when there is another conductor adjacent to it, grouped next to it. That's going to do the same thing. If it's under load at the same time, and a good amount of load, then there's going to be this point here where there is a conflict between the air. Air is where obviously the thermal energy will travel, escaping the conductor to allow it to cool down, to allow it to carry current. If we inhibit or disable the ability for it to give off this temperature under load, we're going to restrict its capacity of current. If you look at table 4C1, This is the one that we're going to look at in a minute. But if you look under there, there's like 9 notes to that table. One of them tells us if the load is something like less than or equal to 30% of the fundamental of all the others, like an off-peak circuit or a harmonic circuit or something, or an auxiliary circuit or something, then it could be omitted from this exercise because it's not going to be under load. It's going to be under the challenge to give off that thermal energy. It also tells us if I have a conductor and the next conductor is 2 times its size away, so like there's another one and there's another one. If the next conductor is twice, you can fit 2 of that conductor between this gap, then that's fine because there's that space there to give off the thermal losses between the 2 conductors. If this gap is narrowed or you drop one in the middle, you've screwed it up. And we've now got to group this. So this example we're doing here, let's say that we have 4 cables. These cables are all under the same sufficient amount of load, and they're all, let's keep it simple. Let's assume that these are all going to be the 2.5 reference method C. Let's say that maybe it's 2 ring finals. Or maybe this is 1 ring final with line, and neutral, neutral. Yeah, we could call it that. So we have a line, and a neutral, and we've just strapped these together. So that's what we've done, is we've put a zip tie around these, we've tightened it up, and there's no air. There's very little air in between these conductors, and so it's going to start getting really quite warm in this area here. So what we have to do is identify what adjustment we've got to make. So if I go back to table 4C1, we'll see that we're talking about reference method C. So we're looking at the second row, item 2, single layer on a wall or a floor. And when we go to the 4 column, you can see that there is a rating factor, which I will write down here as a CG, because it's grouping, of 0.75. Okay? Alright, just pause the video if you can't see where I found that from. It's column of the 4 circuits, because I've got 4, because they're cables, and single layer on a wall. Now, moving on from that, if I was to think about going back to, you can go back to the 18th edition training on this, we must remember coordination. Now, coordination required us to have an IB which was less than or equal to an IN, which was less than or equal to an IZ. And the IB was the design current, the IN was the rated current of the nominal protected device, and the IZ is the cable's current carrying capacity. And we had to tabulate that first from the formula in Appendix 4, which is this one. If you look here at equation 2, the IT must be greater or equal to IN over any applicable rating factors. In this example, we're just going to go with CG because that's all we're really thinking about right now. So the formula is simplified to IT is equal to IN over CG. Now the IN, let's keep this simple. Let's say that this is a 27 amp cable and a 2.5 mil. So let's just say that this is well, we're calling it a ring, so we'll call that a 32 amp. And we'll call that over CG of 0.75. If I get my calculator up. Okay, so 32 over 0.75 equals 42.666. So 42.7, that's fine. Alright, so that's 42.7. So what's happened is the current carrying capacity has shot up. The required current carrying capacity was no longer 32. It now requires to be 42.7 to accommodate this. Now, bear in mind there's a little bit of allowance here because the ring final does allow an IZ of 20 amp, but not to confuse you on that. Let's just focus on the fact that the conductors themselves have to be able to carry 42.7 amp in this example. So if I want to push this forward, I've got to find a cable that can carry 42.7 amp. Now if I open up table 42A again, we can see reference method C, single phase circuit. The next cable that can carry 42.7 amp is the 6 mil, because the 6 mil can carry 46 amp. So going back to the example we've seen now, where I have 4 cables that I suggested were 2.5, the method of installation grouping them has shot them up to a requirement of 6 mil. Let's look at one of these other examples though, because this is how severe it can get. If I pop up an example image, there we go. This is one of the ones that we saw. There are here, let's zoom that in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 18 line conductors down the left there, and they're all cable tied. At the top of the image you can see all the lines are tied together and all the neutrals are tied together, but we have 18 of them. So we have 18 circuits there, and we're going to have to consider grouping. So if we were to say, look at table 4C1 again, you'll notice we actually have a factor for 16 and a factor for 20, which reference method C, let's keep it simple, that's 0.7 for each. So we could go with 0.7 for 18. If I had an alternative method of installation, which I guess you could say this doesn't look like it's surface clip direct, does it? This looks like it's enclosed in the fuse board there. So we could say that it's reference method A to F. So we could drop that factor down. This is why it's important to always identify the factor. Now, if my installation is, as in this case, on tray, ladder, then we're going to use reference methods E. What we call ladder systems. But in the consumer unit, they are tied together in an enclosure. And that means the reference method has switched from E to B. Enclosed in an enclosure. So we're going to go to the first row, and that is item number 1, bunched in air or on surface embedded or enclosed. 16 is 0.41, so let's get rid of that 0.7. 20 is 0.38, and I want to find something bang in the middle of those because I want 18. So take away 1.5 is 39.5. Add 1, yeah. So I'm going to go with 0.395 to find a middle point between those two factors. So my CG factor is 0.395 in this example. Right, if we go back to the illustrations itself, these are, if I remember the site correctly, these are 25 amp radials, and they were 4 mil, but they were sized, they were obviously low smoke, but they were sized for Voltrop, I believe. But let's just push them up. Let's just double check that. Yeah, let's push them up. So 25 amp cable, that's IN device, and we had a 4 mil installed. And when I looked at this and I inquired about it, there was no, I think there were the radial circuits for a hotel with different rooms. So actually, they may have been 6 mils on 32. Let's assume there's 6 mils on 32. This is still going to prove the point anyway. But let's say they're 32 amp radials, 6 mil, and there's no diversity. There's no consideration of one being on or the other because they're going to individual rooms, individual fuse boards, and individual rooms. So the IN is 32 amp. So IT is equal to IN over CG, which is equal to 32 over 0.39, which equals, get the calculator back up, 32 over 0.39, 82. Jesus, right. We now need to have a conductor to consider carrying 82 amp. Well, Let's see if we can find one. We'll go back to, I've only got here table 42A, so we'll stick with it. But let's move over to the reference method B for inside that enclosure. So reference method B, 2 core cables, single phase, AC or DC, column 4. The next number above 82 is 25 mil, 90 amp. So if I wanted to install my cables this way, tying them all tightly together to accommodate those conductors, and let's not forget, when we see that, it might look tidy, but let's remember that we have got there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 conductors that are all potentially under load, and they all have to be able to give off thermal losses when under load. And when we've got them tied up in this way, the ones inside here are not going to be in any way able to give off a significant amount of temperature under load. And if they are under a good amount of load, these ones in the middle, whilst the ones on the outside are also under significant load, which there's nothing in this example that suggests otherwise, then these ones in the middle are going to suffer. How do we fix that? We increase them to 25 mil. We buy 4 or 5 fuse boards to accommodate all these huge cables, and then we'll allow that method of installation, because there's going to be a lot less thermal losses because their cables are so bloody huge. What's the alternative? The alternative, if you want to comply and have a safe system to BS 7671, is not to do that. Do not zip tie your cables together. Now remember, it did say in the notes, I can't remember exactly which note it was. Hang on, I can probably get the regs up. Get rid of that. Now it said, let's get to the table. Appendix 4 I want. Table 4C1. I can hear loads of these. Right. There we go. We're nearly there. Right. It did say table 4C1. Here's the note. Right. Where horizontal clearances between adjacent cables exceed twice the overall diameter, then no factor need be applied. So take in that information through all those notes, but that one in particular says if I have a space between them twice their diameter, then I don't need to apply a factor. So if we go back to these panels, all we technically have to do is cut that tie and just allow some air between the conductors. If we allow some air between the conductors and we allow them to flap around in that space, that's what the enclosure's there for. That's what the air in the enclosure's there to do. If we allow the cables to freely flap in that space, the air around them will result in no need to derate their cable from grouping. So when you do these consumer units and you think about tying them up, now for a cable management side of it, if you want to tie them up to work with them, you tie them up out the way to then connect them, as long as you then remove the ties and space them a bit in the space remaining to allow them to cool down and to run under temperature effectively, then that's fine. Tie them up for a management perspective and then cut them off. But don't leave them tied up. If you are leaving them tied up, you've got to make sure that the designer has accommodated that back at the cable calculations section. All right. So I hope this has kind of made this issue clear. And as I say, it's good to see Sparks, trying to do good work, trying to show illustrations of good workmanship, and I really do not like to kind of say anything about good workmanship, but we do need to be observant with this potential problem, because this area here and here, you see, look at this, all this space in this panel, and we've chosen to squeeze all the conductors together, put them under load, and they're not going to be able to breathe effectively. Remember, we mustn't go over the 70-degree temperature. Alright guys, well I think that's enough for this video, because I'm about to start coughing my guts up. I will be putting some more content on about calculations and formulas as we go, but I just wanted to highlight this one in particular first, because I just think it's something that we need to just be more observant of, especially on initial verifications. Don't squeeze the cables together unless they've been designed for that. Alright guys, cheers. I'll see you in the next video. Bye.
I will not get lost again. I will not get lost.